Hello everyone, my name is Jeff DuBose, and I'm a graduate student in Prashant Kamat's laboratory at the University of Notre Dame, and today I'll be talking about how ligands influence the excited-state interaction between cesium lead bromide and methylbiologen. So as we know, these perovskite nanocrystals are attractive for a wide variety of applications. But when it comes to photocatalysis, this has been less studied, and a lot of that has to do with these stability issues that are associated with the perovskite nanocrystal surface. So what we wanted to do in this case is compare the electron transfer interaction between cesium lead bromide and methylbiologen, which is a well-studied molecular redox shuttle, for 3 different ligand environments. And so those ligands that we wanted to look at are lake acid allylamine, which is sort of the prototypical ligand system. There's a lot of examples of this in the literature, but it is known to suffer stability issues. We also wanted to look at lead sulfate oleate, which is known to suppress halide ion exchange, which is quite beneficial, but it's unknown if the surface is still active for photocatalysis. We also wanted to look at diiododecyl dimethylammonium bromide, or DDAB, which is known to improve the stability and the quantum yield of the nanocrystals, but it's unknown if this strongly binding ligand could actually hamper excited-state interactions. So in order to investigate the system, we're going to use photoluminescence quenching, which will give us insight into how methylbiologen binds to the surface, and also transient absorption spectroscopy, which will give us excited-state information. So with that, if we take a look at the photoluminescence data, in each one of these traces, you can see the emission of the perovskite nanocrystals without any methylbiologen, and as we sequentially add that methylbiologen, we see a nice quenching in each case for each one of the ligand systems investigated. So what we can do is we can basically take this data, and we can start to actually back out and talk about a degree of complexation between methylbiologen and cesium lead bromide. So if we assume something about the equilibrium, if we say methylbiologen plus cesium lead bromide is in equilibrium with its complexed form, governed by an apparent association constant here, then if this holds true, then this equation down here should hold true and give us a linear relationship. So without going into too much detail, this equation basically relates the fluorescence intensity, the apparent association constant, and the concentration of that quencher methylbiologen. And as we can see in each one of these insets, we see a nice linear relationship, which means that this equilibrium is dominating. So once we do this analysis, what we can see is for lake acid allylamine and for lead sulfate oleate, we have about the same order of magnitude degree of complexation, about 10 to the 6 inverse molar. But when it comes to the DDAB case, we see about an order of magnitude lower degree of association. So what that means is that strongly binding DDAB ligand is to some degree hampering the ability of methylbiologen to bind to the surface. So with this information, what we wanted to do was further probe the excited-state interaction using transient absorption spectroscopy. So in this case, what we're going to do is we're going to use a laser to pump up the system to an excited state, and then probe the system before it's relaxed back down to its ground state. So here's sort of an example spectrum of the lead sulfate oleate nanocrystals without any methylbiologen added, and this nice negative feature here corresponds to electrons and holes that have been excited, and as those electrons and holes recombine, that negative feature disappears and goes to 0. Now once we add methylbiologen, we see largely the same type of signal, but now what's happened is the time scale at which the signal is decreasing has changed. So we can take a slice at one wavelength and all these different time points, and do a kinetic analysis of these signals, which is shown here in the middle for each one of the different ligands. And so here in each case, the black trace is without any methylbiologen. We see a nice decay. This is for the native nanocrystals by themselves. And when we add methylbiologen, we see something very different. We see an initial fast decay and this very long-lived component. Fast decay, long-lived, fast, long in each case. So despite the very different degree of association between methylbiologen that we saw from the PL data, interestingly, each system is showing ultra-fast electron transfer occurring on the timescale of about 20 picoseconds. And also, it's showing a long-lived excited state feature, which decays with about 40 nanosecond timescale. So I think at this point it's interesting to note that other systems like cadmium selenide, when you add an electron acceptor, they show an overall faster decay of the signal. Whereas in this case, we're seeing this nice long-lived excited state feature. And so what that means is once we have the initial electron transfer into methylbiologen, these electrons and holes are slowing down their ability to recombine. So in some way they're bound to each other in some sort of dipole interaction, which is extending essentially the charge separation in this system. And that's happening for each one of these ligands investigated. So in conclusion, what we can see is the ligand system is clearly affecting the binding of methylbiologen to the surface of the nanocrystals. But interestingly, there's a disconnect between the ligand binding, the K apparent, and the electron transfer rate constant, since in each one of these cases it's about 10 to the 11 inverse seconds. So that really means is once we finally get methylbiologen bound to the surface, it goes through an electron transfer step with the same mechanism. Additionally, as mentioned before, we can see in each one of the ligand systems involved, we have a fast electron transfer step and this unique long-lived dipole interaction between methylbiologen and cesium lead bromide. And so really this long-lived charge-separated state should be very useful for photocatalysis, as we're essentially extending the time window at which we can do photooxidation or photoreduction reactions. Thank you.